Okay, now we're starting a new topic. I mentioned at the beginning of Calc 2 that Calc 2 is divided up into 4 different topics. The first one was all these applications of integration, and now the second one is going to be methods of integration. By that I mean different methods of finding antiderivatives. Recall that I said that finding derivatives is pretty routine, and procedural, right? You just learn the product rule, you learn the quotient rule, you learn the chain rule, and you can do most everything quite easily. Going backwards, finding the antiderivatives is a different matter. And so we have a whole chapter devoted to different ways to find antiderivatives. And so let's begin this particular lesson by just reviewing what we've already learned. So this is stuff that we've already been using and learned in Calc 1. Maybe the easiest one is what's the antiderivative of just a constant? Okay, recall that this is the formula for it, and the antiderivative of a constant is just that constant times x plus a constant of integration. Agreed? That's the antiderivative. What's the antiderivative of something of the form x to the r dx, where r is any real number at all? And recall that the antiderivative is what you get by just adding 1 to it and then dividing by it. And then of course adding your constant. Okay? What's the antiderivative of e to the x? Okay, that's easy. That's e to the x. Agreed? What's the antiderivative of e to the, let's say, kx dx? Okay, we could do this one by substitution. We could let u equal kx, and then du is equal to k dx. And so the integral of e to the kx dx becomes e to the u, and then the dx becomes 1 over k du, and so we just get 1 over k times e to the, what's the antiderivative of e to the u? It's just e to the u, so that's going to be e to the u plus c, and finally 1 over k e to the kx plus c. Well, I guess I did it. Okay, so there it is by substitution. Sometimes it's easier just to kind of think about it and do it by inspection. But anyway, I did it. There it is, 1 over k e to the kx. So there's that one. Always add your c. Oh, let's see. What are some other ones we know? Let's do another one right away. What's the antiderivative of 1 over x dx? I should have mentioned up here that this works as long as r is not equal to -1. If r is equal to -1, that's the one case where -1 plus 1 gives you 0 down here. Agreed? So you can't divide by 0. So the one time when you can't do this is here. So we have to look at that one separate. What's the antiderivative of that then? It's not this. What is it? So recall that that's just the ln of x plus c. And at this point, this might be a good time to mention that we can get a little better answer than that. Instead of that, let's make note of something here. Here's the question I'm going to ask you. What's the derivative of the ln of the absolute value of x? What is that? Well, let's see. If x is positive, then the absolute value of x is equal to x. And so if x is positive, so let's go like this. If x is positive, then it's going to be equal to the derivative of the ln of x, and the derivative of the ln of x is just equal to 1 over x. This is when x is positive. Agreed? So we've got that. Let me write that a little bit better. That's a little better. If x is greater than 0, then the absolute value of x is equal to x. So the derivative of the ln of absolute value of x is equal to the derivative of the ln of x that's positive, which is just equal to 1 over x. On the other hand, if x is less than 0, then we know if anything is less than 0, the absolute value of it is the opposite of that number. So in that case, the derivative of the ln of the absolute value of x is equal to the derivative of the ln of negative x, if x is negative. And using the chain rule, what's this? The derivative of the ln of anything is 1 over that thing times the derivative of that thing, which in this case is negative 1, and those cancel, and we get 1 over x again. See that? So for either x positive or negative, we see that. So we can say for all x not equal to 0, the derivative of the ln of the absolute value of x is equal to 1 over x, which means that the antiderivative of 1 over x is just the ln of the absolute value of x plus c. So that's a better answer than this, because this one, notice, has a domain which is twice as large, right? This is just the positive numbers. This is the positive and the negative numbers. So the best answer for this then is to write it like this. If you already know, because it's some sort of applied problem, that this thing is positive, then it doesn't really matter. But in general, there's your most comprehensive answer. Okay, good. So that took care of that little one. What are some other ones? Remember these? What's the antiderivative of the cosine of x? That is the sine of x. Agreed. And the antiderivative of the sine of x is the negative of the cosine of x. So you have that one. Let's see, there are a few others that are kind of important. What's the antiderivative of the secant squared of x? That's equal to the tangent of x plus c. Another one that I remember is the antiderivative of the secant of x times the tangent of x is equal to the secant of x plus c. All of these are gotten just from the fact that I know the derivative of this is this. The derivative of this is this. And two more, which we'll also play with a little bit. 1 over 1 minus x, the square root of 1 minus x squared. What's the antiderivative of that? That, recall, is the arc sine of x plus c. And the antiderivative of 1 over x squared plus 1 dx is the arc tangent of x plus c. Those are the main ones that I use. There are a few more, and there's some involving hyperbolic trig functions and things like that as well, which are sometimes important, but these are the ones I personally think are maybe the most important to know. And then if you need to know the other ones, you can look them up as you need them. See if there's any others here I want to mention. I think that's it. So let me just, now that we have this, let me leave. I'll just leave this bottom one here. I won't do it for both of them. I'll do it just for this one. Let's see how we can take this and we can extend it to something more general. And one thing you learn when you take a calculus course is you learn how to read tables, because there's books that have tables and tables of antiderivatives, and especially before you had computers that had all this stuff at your fingertips. Most any engineer or someone who was taking a course in this stuff would have a book of tables, not only with trig tables and things like that, but it would have all sorts of tables of antiderivatives. And then you after a while forget about how to do it. You just accept the word of someone who's already done it, and you get the answer. But anyway, let me show you how some of these things are done. So we know that this is true. We proved this back in Calc 1 Essentials. So if you're kind of interested in how we prove that this is equal to this, go back and check that out. It was kind of a fun thing to prove. But let's see how we can go from here to here. And so here's the way you do it. You force it, okay? I need to have a 1 there. So let's force it. Let's factor the a squared out in front, which means I can then write this as x over a, quantity squared, plus 1 dx. Do you agree I can do that? Because if I bring this a squared back in here, those are going to cancel. I'm just going to end up with an x squared there, and then I'm going to get a squared times 1 is a squared. So that's true. And so I did 2 steps in one. I divided this x squared by a squared, and then I wrote it as x over a. And the reason I'm doing that is because now I'm going to make a substitution. Okay, I'm going to let u be equal to x over a. So du is equal to 1 over a dx. And so this thing just becomes what? It's going to be 1 over u squared plus 1 dx. Notice if I solve it for dx, dx is going to be a times du. So the a can come out front, and now I have my du right there. And now this becomes 1 over a, and this is just the antiderivative of 1 over u squared plus 1, which we know is just the arctangent of u plus c. And finally, you can plug that back in and get arctangent of x over a plus c. So there it is right there. So that's a really convenient one to know. You can do something similar with the arc sine, and if you do something with the arc sine, you can prove this. I'll leave this one for you. Do a squared minus x squared dx is equal to, let me just check the table myself, is equal to the arc sine of x over a again, okay, plus c. So those are kind of nice to know, okay? If you needed to, you could derive them each time you want them, but that's those are nice ones to remember. Okay, let's do just a couple more problems in this general section. Back in Essentials of Calculus, we learned the method of substitution, and so let's just do a couple of them just to remind ourselves how that works, because what we're going to do from now on is going to learn lots of other methods as well. But substitution was the first one we learned, and that's just so kind of fundamental that we learned it already in as soon as we learned about antiderivatives. Here's a couple of my favorite problems. Here's one of them. I don't know. See if you can see why I like this one so much. This is antiderivative of x times the square root of 1 minus the ln of x squared from 1 to the square root of e. Okay, boy, isn't that an impressive looking thing? Look at that. Well, that's just begging to be solved by way of a substitution, because you look at that and you say, I can't see any way to solve that one. And the thing that really bothers you is the fact that you've got an ln inside that square root. So you really want to get rid of that. So let's see if we can. We'll let u be equal to the ln of x, which means that du is equal to 1 over x dx. And so this becomes 1 over the square root of 1 minus u squared. So I took care of this. That's what I wanted to do. Now what do I have left? I have a dx there that I always have to change into a du. Let's see how I change it into a du. Dx times 1 over x is equal to du. Well, I made up the problem, and that's why I made it up to look this way. Look at here. Dx times 1 over x. 1 over x dx, that's exactly du. So I've got that just the way I wanted it. See that? Now we need to change the limits of integration. When the dummy variable here, when x is equal to 1, the ln of 1 is equal to 0. The dummy variable x here, when it's equal to the square root of e, the ln of the square root of e is equal to 1/2 the ln of e, which is equal to 1/2. So that's 1/2 right there. Now we can take the antiderivative. We've changed our limits. This, recall, is the arc sine. of u evaluated from 0 to 1/2, which is the arc sine of 1/2 minus the arc sine of 0. Arc sine of 1/2, that means I want the angle whose sine is 1/2. That is pi over 6. What's the angle whose sine is 0? That's 0. So pi over 6. There we go. Okay, so there's that one. One of my favorites. Let's try two more. Okay, here's another one I like. X plus 1 over x squared plus 1 from 0 to 1. Okay, I like this one because it just kind of looks tempting. You want to do some dividing or something, but you can't. You can't divide, but what you can do is to break it up, right? I can break up the numerator and write it as x over x squared plus 1 dx plus 1 over x squared plus 1 dx. Okay, and now I can make a substitution here. Let me do it over here. I can let u be equal to x squared plus 1. So du is going to be 2x dx. So this integral becomes the integral of u on the bottom. X dx is 1/2 du. There's your 1/2 du. You can change the limits of integration. When x is equal to 0, u is going to be 1. When x is equal to 1, u is going to be 2. So you have that. And that's just going to be the ln of u from 1 to 2, which is equal to the ln of 2 minus the ln of 1. Of course, the ln of 1 is equal to 0. So you got all that stuff. What about this side? We just remembered that the antiderivative of this is the arctangent of x from 0 to 1, which is equal to the arctangent of 1 minus the arctan of 0, which the arctan of 1, that's the angle whose tangent is 1. What's the angle whose tangent is 1? That's pi over 4. What's the angle whose tangent is 0? That's 0. So we end up with the ln of 2 plus pi over 4. Okay, there you go. Okay, very good. Let's just do one more, as I say, just to kind of remind you how these things work. I don't know, we could do maybe a couple, but if you have, let's do this one. Let's do x times the square root of x minus 1, where x goes from 2 to 5. How about that? Okay, how would you do that one? Let's make it x squared. Let's make it x squared. How do we do that one? Well, I look at that and I say, oh, the thing that bothers me there is the x minus 1 inside the radical. So let's see once if we can get rid of it. The fun thing about integration, finding antiderivatives, is you seldom know ahead of time if it's going to work. Once you've done it for 20 years or 40 years the way I have, then you do, but at least at first you don't. You just got to give it a try and see once what it works. So that's why it's almost like doing math research. So this is going to be du is equal to dx. And now what happens here? I'm going to get the square root of u. That's this. Dx is du. That's just a quick changeover. No problem there. Now I have an x squared left. So the only reason that this whole method is going to work is if I can get everything in terms of u. Can I do that? Sure. I can set that x is equal to u plus 1, and so x squared is going to be u squared plus 2u plus 1, right, when I square that out? So I guess I needed a little more room here. I needed a u squared plus 2u plus 1 all times square root of u du. And then again, we need to change our limits of integration. When x is 1, when x is 2, u is going to be 1. When x is 5, u is going to be 4. See that? After a while, you can make these things up in your head, just like I made up this one. You can kind of see the end from the beginning. Let me make sure that everything is still going strong here. My computer, yep, very good. Okay, so let's see. So now, what can I do? Now I can multiply this all out. This is going to become u to the 5/2 power plus 2u to the 3/2 power plus u to the 1/2 power, all du from 1 to 4. And then, of course, you can actually take the antiderivative. We haven't taken the antiderivative yet. So it's going to be what? U to the 7/2 times 2/7 plus u to the 5/2 times 2/5 times 2 is going to be 4/5. And then plus u to the 3/2 times 2/3. So there they all are. Evaluate that from 1 to 4. Oh boy, is it worth doing? Let's see if I can do it. 4, let's see. I can first take the square root. The square root of 4 is 2. 2 to the 7th is 128 times 2 is 256. So it's going to be 256/7. Plus, put a 4 in here. The square root of 4 is 2. 2 to the 5th is 32. 64, 128, 128/5. Like so. Square root of here is 2 to 8, 16/3. So you have all that. Now you stick in a 1 and you're just obviously going to get 2/7 plus 4/5 plus 2/3. So there you go. Okay, do the subtraction and you got it. So there's that one. Okay, so that's almost the end. I just want to show you one more, which is going to lead into the next lesson. Okay, lead into the next lesson. Let's do these right here. How about x e to the x squared? Oh, you know what? I forgot to do these. Let me just remind you of this. What's the cosine of kx dx? You can do that one with the substitution just like we did e to the kx. That's going to be 1 over k times the sine of kx plus c. And similarly, the antiderivative of sine of kx is going to be minus 1 over k times the cosine of kx plus c. So I remind you of those. So now, what about this one? Let me give you a couple here. And here's the other one. Okay? Look at those. This one looks easier than this one, agreed? This one's got an x squared there. This one's got an e to the x. However, let's just see once if we can solve either one of them. This one can be solved just by letting u be equal to x squared. And so du is 2x dx, agreed? So this just becomes the antiderivative of e to the u. And then you have x dx left, and that x dx is going to be 1/2 du. And the antiderivative of e to the u, of course, is just e to the u. And so that's going to be 1/2 e to the what? E to the x squared plus c. See how that goes? So there's that one. This one looks easier, but I'll challenge you to try to figure it out. Try to figure out the antiderivative of that one. Even though it looks easier than that, try to find the antiderivative of this. Come up with some sort of function whose derivative is this thing. Sometimes when people see it, they might naively say, well, I'll just take the antiderivative of each one of these parts on its own, right? The antiderivative of this is this, and the antiderivative of this is this, and so I'll just multiply them together. That works as long as we're adding, right? If I gave you x plus e to the x, then the antiderivative of that is going to be 1/2 x squared plus e to the x plus c. Adding or subtracting, that's fine. If you have a constant in front, you can just pull it out front. Not a big deal. But as soon as you multiply, then it's different, because if you took the derivative of this thing, you just take the derivative of each one in turn to get those back again. But if you were to take the derivative of this thing, you'd have to use a product rule, right? And as soon as you use a product rule, there's no reason to think you're going to end up with that. In fact, you won't. Okay? So that's where we go in the next lesson then. We learn how to find antiderivatives of things like that. It's called integration by parts. It's one of the coolest, I think, one of the coolest methods of finding antiderivatives. It's kind of doing the product rule in reverse is what it is. So that's what's coming up. So that's on the next lesson. See you then.